Hello. In today's lesson, we're going to talk a little bit about logarithmic scales as they appear in the physical sciences. So I've got examples from many of the physical sciences today. We've got stuff from chemistry, from physics, from earth and space, which basically covers all the real sciences. I mean, not biology, because, I mean, come on, biology is not a real science. If you're a biologist, I'm sorry, you're wasting your life. You're missing out big time. Okay, I'm kidding a little bit, but not really. So today we're going to actually look at three very realistic scales that you would encounter if you took a course in chemistry, if you took a course in physics, or if you took a course in earth and space science. And let's start in with our chemistry example, which is the pH scale. Now, most of you were just fine working with the pH scale or talking about the pH scale in earlier chemistry courses, but you probably didn't really understand the true actual detail of how the scale worked. So most people know that pH, I'm going to skip the definition for a second, but most people know that pH is neutral when it's 7. Anything below 7 is acidic and it goes down to about 1. And anything that is alkaline or basic is anything above 7 up to about 14. Now, technically, the pH scale can go a little bit lower than 1 or above 14. However, it's extremely unlikely because of the super potency of acids and bases at that point. So it's more of a real life physical limitation. It's kind of hitting as much as it can be as opposed to mathematically it stops at 1 and 14. But anyway, the definition of pH, I'm just going to put a little box around it up here. It's the negative of the logarithm of the hydronium ions. So basically the H plus ions. And, oh, I just realized I'm down in the bottom corner there. Ooh, I'm guest starring in this video. Okay, let's do that. Um, Now I'm distracting myself. Sorry, I'm gonna actually go to just get rid of me. There we go. Okay. So hydronium ions essentially, when you take water, neutral water, H2O, so you're getting some chemistry lesson here too today. When you take H2O, it can break down into H plus ions and OH negative ions. If there are too many H pluses, you get something that's acidic. If there are too many OH negatives, meaning there are very few H plus ions, you get something basic. And we're talking about concentrations that are usually decimal places, 0.0000 something. Um, but when we express a number like 0.000 something in base 10, that's really 10 to the exponent negative some number. And according to the power rule, we can bring that exponent with some number down in front, which will always be a negative because we're dealing with concentrations less than 1. And that negative in front will then cancel out the negative and we're left with a whole number, like 1 through 14. So basically the scale is a lot nicer to work with than saying, oh, I've got some liquid over there that has a hydronium concentration of 3.28 times 10 to the negative 4 um, moles per liter. I mean, that's a horrible way to say it. So we just say stuff like it's got a pH of 4. Much easier to work with. On the screen here, I've shown you a little scale showing several common items that you might see or know about and their approximate pHs. So we've got everything from car batteries, or technically any battery, but car batteries tend to be the ones that we talk about with really harsh pHs, very acidic. Stomach acid, which you know is very acidic. And then a whole bunch of other stuff on there like vinegar and coffee, water, of course, being in the middle is neutral, and a whole bunch of other things. Now you'll notice that on the top there we do have stomach tablets, which are the things that neutralize stomach acid. So it makes sense. Stomach acid is neutralized by a base. And then we get stuff right up to like drain cleaner and bleach, which are pretty nasty bases or pretty nasty alkali materials. So let's just approach a problem here and see how we can do this using what we know. And we know that tomatoes have a hydronium ion concentration of approximately 0.0001 moles per liter. What is their pH? Now, I could cheat and just look up on the table there because it looks like tomatoes have a pH of about 4, but let's actually do the math. So we're told that the pH, and I realized I didn't leave a lot of room here. It's because I wanted to keep the table on the page as long as I could. pH is equal to negative the log of the hydronium ion concentration, which is 0.0001. Now, I can actually just punch that into my calculator. There's nothing wrong with it, but I think it's a little bit more obvious if I do it this way. I can write 0.0001 as 10 to the negative 1, 2, 3, 4. And now, according to my power law, I can bring that negative 4 out front. So it's negative 4 log of 10. And log of 10 is just 1. Log base 10 of 10 is 1. So that just becomes 4. Which is exactly what the chart above us told us. So that's where the negative in front comes from. It gets rid of the fact that the exponents on 10 are actually going to be negatives because we're dealing with numbers less than 10. In most cases, much less than 10. Yeah. And it gives us nice numbers. Much easier to work with pHs than it is to work with the hydronium ion concentrations. Blood has a hydronium ion concentration of 4 times 10 to the negative 8 moles per liter. Is blood acidic or alkaline, and what's its pH? Okay, I can really quickly, by just looking above, say that blood's up there around 8, so it's definitely going to be alkaline. But for its pH, we're going to do it the same way we did the other one. pH is negative log, and then the hydronium ion concentration is 4 times 10 to the negative 8. Now this one, because it's not a nice power of 10, I mean, it looks like it's 10 to the negative 8, but the 4 kind of messes that up. Now we pull out our calculator, and I'm just going to punch in 4 times 10 to the negative 8. And then I'm going to hit my log button. Please keep in mind your calculator, you may have to hit the log button first. But either way, once you've taken the log of that, you get out negative 7.4-ish. And the negative sign in front is going to make that a positive. Okay, so even though our table shows blood at 8, the pH of this particular blood sample is actually closer to 7.4. It's a little bit closer to neutral. And I'll point out that most of these aren't set in exact values. It's not like all coffee is exactly 5 pH. Some will be higher, some will be lower. Same thing with most of these. Let's take a look at this last one here for this application. That's part C. And that's a cup of coffee has a pH of 5.5. Stomach acid has a pH of 1.1. How many times higher is the hydronium ion concentration in the stomach acid compared to the coffee? Wow, that's pretty big. What I'm going to try and do with this one is logic your way through it a little bit. Because it's actually easier to do with logic than it is to do with mathematics, and it's good to practice this kind of skill. And besides, this is just one application anyway, so when it comes to applications, every application is a little different. Let's try a different method of solving. So I'm going to point out that if I want to go from a pH of 1.1 to 2.1, the hydronium ion concentration is going to change by a factor of 10. In fact, it's going to be 10 times less concentrated. As we're moving towards the bases, we have less hydronium, so we're going to have 10 times less. If we go to 3.1, because every time we go 1 on the scale, it's going to be 10 times bigger. That's how logs base 10 work. And then to 4.1, and then to 5.1, and then we could go to 6.1, but we only have to go to 5.5. So this is going to be 10 times. Now, technically it's 10 times smaller, but let's just focus on the number. We'll worry about smaller or larger afterwards. So it's 10 times larger, 10 times larger, 10 times larger, 10 times larger, and I don't know, a bit. But here's the key. Every time I go up by 1, I get the power of 10. So here I'm going up by 1, 2, 3, 4, 4.4 jumps. So that's actually the power I'm going to put on 10. That last jump from 5.1 to 5.4 is not 10 times bigger. It's 10 to the 0.4 times bigger because it's only 4/10 of the way along the magnitude. 10 to the exponent 4.4. I know it's going to be over 10,000 and less than 100,000, but where exactly in between, I'm not sure. My calculator says it's 25,119. I'll round off there. And the hydronium ion concentration in stomach acid compared to coffee. So we're comparing stomach acid, which means the hydronium concentration is higher. So therefore, stomach acid has a, I don't feel like writing out the word hydronium, H plus concentration 25,119 times higher than coffee. Okay, so we're talking much, much stronger. And now I think you can see why on a pH scale, you want it to be logarithmic and not linear because you don't want to have to deal with things that are thousands, millions, billions times bigger than other values. Okay, let's move away from chemistry, much like I did in university, towards physics. And we'll talk a little bit about the decibel scale. Now the decibel scale is a little bit weird. It compares ratios of two sounds. We'll call them I2 and I1. You can technically use this for to get like a finite number, but it's usually easier to talk about changes of decibels versus how loud is one sound versus another. It's really kind of hard to define the initial sound, the zero sound, because there's no real such thing as zero vibration. If you've taken science, you probably are aware that all molecules move, therefore all molecules are giving off some sound. Most sounds are so quiet we'd never hear them. Like no one's hearing any atom jiggling in their ear, but they're there. So we can talk about ratios of sounds. And there's our equation for it. If we have two sounds, their decibel rating. So I'm gonna try and be really clear on this. There's the decibel rating for sounds, and then there's the intensity of the sound, which is actually measured in watts per square meter. So basically, that's just saying how much energy goes through a square meter of space. The more energy, the higher the intensity. So our equation is the decibel rating of the second sound minus the decibel rating of the first is equal to 10 times the log of the second sound's intensity divided by the first sound's intensity. Very confusing. If you're kind of a little lost here, that's okay. That's why you can refer back to this table and that equation anytime you'd like. The key feature here, though, is that every time you go up 10 decibels, every time you add or subtract 10 decibels on the decibel scale, the sound intensity is 10 times louder or 10 times quieter. So going back to pH, every time you went 1 on the pH scale, it was 10 times more or 10 times less. Now it's every time you go plus or minus 10, it's times 10 or divide by 10. Now the reason for that is you're actually going up by 1 or down by 1 bell, but we don't tend to measure in bells. We measure in 1/10 of a bell, also known as a decibel or a decibel. So what that means is if I just draw on this table a little bit, if I go from, say, for instance, a sound of 120 right here, and I go up to 140, it got 10 times louder and 10 times louder again. So 140 is 100 times louder than 120. And that's actually going to be true for 60 to 80. It's the same jump. We went up by 20 decibels, which means we're going up by a sound intensity of 100 times 10 times 10. And that's really the part to understand. When you're going up and down on the decibel scale, every 10 you go up or 10 you go down will be multiplying sound intensity by 10 or dividing sound intensity by 10. Incidentally, I want to point out to you up here that going to see a band is very close to the threshold of pain, and in some cases slightly above the threshold of pain, especially when you're old like I am. I actually went to see my favorite band a couple years ago, and I had to buy earplugs to wear into the concert because it actually was physically painful to be in there. All right, so here we've got a whole bunch of decibel ratings for different sounds. 0, by the way, is not the quietest sound possible. 0 is the quietest sound possible, the quietest sound that the average individual can hear. You can actually have negative decibel ratings. It just means, like for instance, a decibel rating of -10, if you went down below that, just means it's 10 times quieter than what most people can hear. It's not actually negative sound, it's negative decibels, which is just a lower sound intensity. So for instance, if I wave my hand back and forth, that's pretty quiet, but it might actually give off a little bit of vibration, a little bit of sound through the air that might be -10 or even -20 decibels. Not enough for the average person to hear, but enough that it exists. And likewise, just because 0 is the threshold of hearing for the average individual, someone who's hard of hearing might have a threshold of hearing of 20 or 30 or 40 decibels before they even hear anything. And likewise, so someone with really keen hearing might be able to hear -5 or -10 decibels. Okay, so now let's actually try to solve some problems. Again, I think it's much better with situations like this to think about jumps than it is to think about the actual equation. Not that you can't use the actual equation. For this one, actually, let's try it first and then go back to the equation and see if it's any better. So how many times as intense is a normal conversation compared to a whisper? Well, if we start off with the whisper and we go up in jumps of 10, so 30 decibels, 40 decibels, 50 decibels, 60, and then the last one's 65, which is not a full jump. This is 10 times louder, 10 times louder again, 10 times louder again, 10 times louder again, and part of that 10, but either way it looks like it's 4.5 jumps. And 10 to the exponent 4.5 is 31,623 times as intense. So even though it's only 45 decibels higher, it's 31.6 thousand times louder as far as sound intensity goes. Now to go back to our actual formula up here, we could try that. Decibel rating 2 minus decibel rating 1 equals 10 log I2 over I1. Decibel rating 2 minus decibel rating 1 equals 10 log I2 over I1. Well, the difference in decibels was 45. Left the O out of the log. Divide both sides by 10. And what this is really saying, this 10 does, is it switched us from 45 decibels to 4.5 bells. And then I can rearrange that by putting it into exponential form. And I realize I'm running out of room, so I'm just going to kind of write it up here. If I put that in exponential form, it's 10 to the exponent 4.5 equals I2 over I1, which is 31,623. And I'm not solving for I2 or I1. I'm just saying I2 is 31,623 times louder than I1. So I've actually finished it at that step. And I'm going to put therefore, and I'm not going to write it because I'm literally out of room there, but therefore, I'll say it in words, the intensity of a conversation, a normal conversation at 65 decibels, is 31,623 times louder than a whisper. Part B. The cheapest dishwasher for sale at Lowe's is 55 decibels. The quietest dishwasher you can get is 40 times quieter. That's how they advertise it. It's 40 times quieter. What is the decibel rating of the quietest dishwasher? Okay. So this one, I'll start with the equation and then we'll see if we can logic our way through it. So decibel 2 minus decibel 1 equals 10 log I2 over I1. Well, in this case, we're talking about 40 times. We just have to make sure we're consistent with which one is which. Let's use the 55 decibels as the second one, the 2. Actually, no, let's use it as 1. B2 minus 55 equals 10 log. Now, if B2 is going to be quieter, then I2 over I1 should be a fraction. Sorry, B2 is quieter, so I2 should be lower. So we're looking at a fraction over 1. So it's going to be 1/40th. It's 1/40th the intensity. And now I can just plug that right side into my calculator. The log of 1 over 40 is negative 1.6. Multiply that by 10. B2 minus 55 equals negative 16. 0.02, but we'll just say negative 16. And then we'll add 55 to both sides. B2 equals almost exactly 39, even with our little bit extra there. So that means that the quieter dishwasher is actually going to be 39 decibels. Therefore, the quieter dishwasher will be 39 decibels. Is that really a big difference to most people? Not particularly. By the way, I talk about real-world applications. This is a real-world application. At the time that I wrote this question, I actually was searching for a dishwasher because mine broke, and those are the two I was looking at. The cheapest dishwasher versus the quietest dishwasher. And I realized getting the quietest one was not worth the extra money. And the one I have is beautiful. I love it. And I would tell you which brand it is, except that I would feel like a corporate salesperson. Okay. You know what? I don't think we need to logic our way through that one anyway. The equations seem to work just fine. Let's move along so we can speed up this lesson into our final application, which is the Richter scale, the scale which is used to measure earthquake magnitudes. Now, I'm going to blow some of your minds here, but when you hear about earthquakes and you talk about its measurement on the Richter scale, they don't actually use the Richter scale anymore. It's actually called the moment magnitude scale, but it's essentially just a Richter scale that's been tweaked to be slightly more scientific. It has to do with how it's actually measured, but it's done the same and it rates the same. So we still call it the Richter scale. Yields pretty much the same numbers. So the magnitude M of an earthquake is measured using the Richter scale, which is defined by M equals log of I over I naught, where I is the intensity of the earthquake and I naught is the intensity of a standard low-level earthquake. I got to be honest with you, I'm not sure I even understand exactly what that means. Some base vibration in the ground. So the magnitude of a standard low-level earthquake, if we try, not the intensity, but the magnitude, would be what we get if I is I naught. So we get I naught over I naught, which is log of 1. And what what number do we put on, or what exponent do we put on 10 to get an answer of 1? And the answer is the exponent would be 0. So an earthquake of magnitude 0 is what defines our standard low-level earthquake. And then everything else is measured as related to that. Now, on the Richter scale, every time I gets 10 times bigger, the log of it actually will go up by 1. So every time we go up 1 on the Richter scale, there's 10 times more intensity. I will point out that if you do actually go into earth sciences, there's also a measurement of energy, which is different than a measurement of intensity. Intensity is basically talking about how much shaking is there. Energy is how much energy is released by the earthquake. Intensity is base 10 log, and energy is not. I'll leave it at that. But we're just going to consider the intensity because it's easier to deal with. And it's actually what magnitude is based on. Okay, so what is the magnitude of an earthquake 5 million times as intense as a standard earthquake? Well, the equation's actually really easy to use here. So most people are like, well, which ratio or which number is that? Is that I or I naught? And the answer is yes, it's both, because it is a ratio of the two. So we're not actually plugging in 5 million equals I or 5 million equals I naught. We're plugging in 5 million equals I over I naught. So we just take the log of 5 million. Sometimes it's nice that you leave the best for last, or the easiest for last. So log of 5 million would be a magnitude 6 point, we'll round to 1 decimal there, 6.7. So over here it would be between strong and major earthquake. So yeah, that's a pretty significant one. It's not destroying a continent, but it's definitely messing up a city or two. Part C. The largest earthquake in Ontario was a magnitude 4.4 in Rayside, Balfour. It's like I've never seen a French word before. Rayside, Balfour in 1984. And by the way, this is true. Everything in this question is true. The largest earthquake ever recorded in the world was a magnitude 9.5 in Valdivia, Chile. I hope I'm pronouncing that correct. In 1960. How many times more intense was the Valdivia quake relative to the Rayside Balfour quake? Okay, so here's how I want you to think about it. Every time you go up by 1 on the magnitude scale, you're multiplying by another 10. Well, if we're going from 4.4 to 9.5, we're going up 5.1 times. That doesn't mean it's 5.1 times more intense. It means that when we go up by 1, it's 10 times bigger. 2, it's another 10 times bigger. 3, it's another 10 times bigger. 4, it's another 10 times bigger. 5, it's another 10 times bigger. And then that extra 0.1 is a little bit more. But either way, the intensity is going to be 10 to the 5.1. And when we punch that into our calculator, 10 to the 5 is 100,000. But 5.1 gives us 125,893 if we round off to whole number. So that means that the world's largest earthquake shook with over 125,000 times the intensity of the largest earthquake in Ontario. And what does that tell us? It tells us that we got it pretty good in Ontario because we're not dealing with nasty, nasty earthquakes that are trying to destroy us. It's part of the advantage of living inwards of the Canadian continent, or the North American continent, which is pretty solid, at least where we are. All right. Again, before I send you off to do the homework on this one, I'm going to remind you that Today it was not about memorizing or learning an equation that you have to use all the time. It's about looking at scales or specific examples of logarithmic ideas. And every application is going to be a little bit different how you apply it. It's more getting your thinking into the right state of mind, thinking logarithmically and exponentially.